Hello, hello, hello. All right, so I did get another email, but it still didn't come in with sound in it from Ross. And I got a presentation sent to me by Tyler, but I couldn't access it because I went to an account I didn't have access to. Let's see, what's my password for this one? Too many accounts that I've used in the past. Yeah, that one still hasn't come through, so I'm still not sure what that one's at. So did you check your email just now, Tyler?
In the process of it, it's me that.
It should have sent you an email of me requesting access to that folder from my MPCC account, MPCC thing.
Google's really pushing the Google Plus thing, and it's getting annoying.
Yeah, they are. So but those are the only other presentations I've received so far. So unless we have something I didn't see here, and I'll check one more time, and we're done with presentations. Wrong password.
There, I think I got it.
So I have PowerPoint. Yeah, the latest one I got from you, Ross, didn't come through with the sound attached to it. So after you do the sound, you have to save it still. I don't know if that's what you forgot to do or not, but I did get your PowerPoint reviews. So everybody should have emailed me your reviews of the other two presentations we saw. Of the two presentations we saw. Okay, so now we need to move on to, so I send you out stuff so that you can make a transmitter. What I really want you to do with the radio transmitter is I want you to be able to send something and receive something with both your transmitters. Now, with your transmitter and your receiver, your radio receiver. I think that we probably need to move on with life and not grade that portion of it. So if you want to do that, you can go ahead and do it, but we're kind of moving right along here. We've got a new project to do, and it's fairly complex. So let's take a look at our hydraulic arm project here. Okay. So I have three documents I think that I'm going to send you here, where you're going to learn about pneumatics and fluid power. And these are essentially workbooks. You're going to be learning some things, and you're going to be doing answering some questions and doing some activities, all about hydraulics. And I will send these to you in an email. And you have lots of different things to do here, including a little bit of math that's not terribly difficult. So it shouldn't, I hope, be too much strain on you. If you have any questions, of course, you can talk to me. But we're going to learn about some different laws of fluids and some different ideas with fluids. And we're going to do some simple calculations. And some, let's see, here's the first activity that they have. So here we have an activity where we're actually going to put together a little hydraulic system. And we're going to be able to do an activity and write down our results. Here they talk about viscosity, and then they do a very basic hydraulic system to lift a book. Okay? And then they talk about some work and mechanical advantage. So this is fairly involved. It's got, I don't know how many pages, it's got 19 pages on it. And it's a fairly complicated deal here. This ends up with an invention that you're going to make that uses fluid to power it. In other words, uses hydraulics or pneumatics. And it's going to have to do one of these things: open a jar, crack an egg, or toss a ball. Now, when you're doing this kind of thing, you definitely want to go simple as you can. The more complex it gets, the more problems can be, more holes can be poked in your invention. But in the end, after doing all these activities and all these different kind of homework type problems, you're going to make your own little invention at the end of it. 19 pages long. So you will have until Wednesday to work out that. Now, it's a fair amount of work as far as sitting down and writing things, but you don't actually have to build anything very complex to get that done. It's mostly basic beginning stuff. The second one I'm going to send you is called the hydraulic arm, where you're going to actually put together a hydraulic arm from the materials that I've given you. Now, I think that you should have the proper number of materials for this particular project. It looks like it requires quite a few dowels, which I didn't provide for you. And is this actually the arm I want you to do? Let's actually look at the different one. There's a different one I want to look at. This one is the very advanced arm. No, that's not the one I want to do either. So I want to do this one. So this is the second one. This is the second page of the paper I'm going to give you. It's also 19 pages, and they have you using these plastic arms and dowels and everything else, but you're not going to necessarily have all the parts left over to do this. So you're going to have to decide what substitutions you're going to make and how you're going to use the parts that you do have to accomplish this task. They're giving you an example of what can be done, and essentially your design is going to have to be very close to this in order to get this, to make this thing. But the end result, if we go all the way to the very end of this, is a hydraulic arm that can pick up something like, let's say, a deck of cards, or something similar in size and weight. You know, it's about a little bit less than a quarter pound, or so, about a quarter pound of weight. But it can do it by being remotely controlled. Remotely meaning there are tubes connected to some syringes that you're going to manipulate, and you're only going to manipulate the syringes at one end of the tubes, while at the other end of the tubes your machine is going to be doing this work. Right? And so I've got these two sets of paperwork to send you. One of them is a learning guide, essentially. The other one is a project guide for this hydraulic arm project. And while they give you precise instructions here, I have not given you the materials to follow these precise instructions. So you're going to have to now take the initiative and modify these instructions and redesign so that it will fit the materials that you have. Again, a very important engineering process. To be able to take something that somebody else has done, a design that somebody else has made and given you instructions for, and to adapt it into your situation. So this is, you could think of this as a reverse engineering process almost, where you're not doing all the original design, but you're kind of doing a redesign and fixing it to fit what you can provide. And I've given you a lot of materials for this, but not the ones that they called for, like I said. So I expect that everybody's design will be somewhat different, but that they will all accomplish the same kind of thing, right? So we will, I will send both of these documents to you, and it will be your job to complete the first one by Wednesday. It's mostly written work and just a little bit of experiment. And then the second one, let's see, is that right, by Wednesday? Actually, the first one I'll have you complete by Friday. So you have this week to complete the first assignment, which includes lots of like written problems and some small experiments. And then the next one will be due before Thanksgiving. So you'll have a week and a day or two to work on the next one. Or if you finish the first one early, you can get started on the second one. Each day in class between now and then, I will be going over different parts of this to help you through it. And so I'll start off with a basic introduction and an overview today. And then on Wednesday, I'll go through some more of the first one. And on Friday, I will show you some hydraulics experiments to give you some more ideas of that. Today, I'll also go through some of the background of hydraulics, so that you can understand the concepts behind it without having to reinvent the wheel or take a whole class on this stuff. So those will be coming to you in your mailbox today, and you'll have a week for the first paper, which is the fluid power, so that's the first week, and then a week and a day or two for a hydraulic arm before Thanksgiving for the second one. And just like always, when you're doing the project, which is next week, not this week, you will have a logbook to take notes in. You'll take notes in your logbook every time you work on your project. You will keep track of all the important things that you do, and in your logbook you include the information from those important things. For example, data, pictures, drawings, equipment lists, so on and so forth. All those things that helped you to figure out the project will be in your logbook, and that logbook will be turned in. So that's what's going on for the next 2 weeks. Now let's take a look at this fluid power worksheet again, and let's learn about hydraulics a little bit. I'm actually going to start off on the internet, and we're going to look at hydraulics in general and what they really are. Okay, so hydraulics are used in lots of different systems. There are so many different systems where hydraulics are used. Probably the most common one is something like this with a tractor, right? You have lots and lots of different kinds of tractors that use hydraulics to control the arms for these bucket loaders and end loaders and whatever, right? And I'm sure that you've seen these pistons on here, and you kind of understand how one piston lifts the arm, another piston rotates the arm, and another piston rotates the bucket, and so on and so forth. You probably understand kind of how that works, but you may not understand what is behind the science here. For example, you see here that there are lots of different components to this, to connect it to each one of these pistons out on this big hydraulic arm. There's these there are these tubes that are connected to boxes and connected to filters and connected to pumps or connected to tanks or whatever they're connected to. You may see all these things, but you may have no idea what's actually causing these pistons to move or what gives them such power. And you may be surprised, actually. The simplest form of hydraulics, of a hydraulic system, is the lift. See if I can get to that. How come that doesn't work? don't know why it's not working. Okay, let's close that. So the simplest one is the lift. And this is a very simple representation of a hydraulic lift. Hydraulics take advantage of a principle called, I think, Pascal's principle, or Pascal's principle. And Pascal's principle states that when you have a liquid or fluid inside of a closed space, and the closed space, the fluid inside the closed space is an ideal fluid. In other words, it won't change volume if you apply a pressure to it. It's not compressible, and it has very low viscosity. And also that the whole system is essentially at the same level. In other words, one end of it's not 100 feet above the other level, the other end of it. It states that when you apply a pressure to one part of the fluid, that pressure will spread itself out throughout the entire fluid. And so we take advantage of this principle in these systems. So in this particular system, we have a little piston over here that has a very small cross section. It's a very skinny piston. Very skinny cylinder, rather, with a skinny piston inside of it. So the piston is this arm that's stuck down inside of here, and the cylinder is, of course, this tube that it's stuck inside of. On the other end of the system, we have a wider piston, or a bigger piston, with a bigger cylinder that it's inside of, right? So it's sticking inside, the pistons is down inside of this bigger cylinder. Well, when we apply a force, and 10 newtons of force is about maybe a pound or a couple of pounds, that's about a pound, a couple of pounds. So we apply a couple of pounds of force on this piston here, push down with a couple of pounds of force, that is going to apply a pressure in the fluid here, and the pressure is going to be equal to the 10 newtons of force we applied, divided by the area of the piston. In this case, this piston is got a 10 centimeter wide radius, so its area is about 0.8 square centimeters. Not very big. It's pretty small. So you're taking 10 newtons and dividing it by a small number. So the pressure is going to be up around maybe 100, what we call newtons per meter squared, or 100 Pascal. Let's say it's 100 Pascal or maybe a little more. That same pressure of 100 Pascal is going to be transmitted through this fluid. So all this fluid is going to be at that pressure of 100 Pascal. But over here, that 100 Pascal of pressure is going to spread itself out over a bigger piston head, or a bigger end of this piston. This one has a 30 centimeter wide piston head, which means it's not just 3 times as big an area, it's actually a 9 times bigger area. And so it has 9 times as much area, 9 times as much pressure pushing up on it, which in the end is going to result in 3 times as much force coming up when we multiply by the area again to get the force. And that's the beauty of hydraulics. Over here we have a tiny little cylinder with tiny little piston and a tiny little force. We apply our tiny little force, just a couple of pounds. And over here with the bigger piston, the bigger cylinder, we have 3 times as much force because it has 3 times the radius. Okay? The trade-off is how much it travels. If we push this one down 30 centimeters, so it goes down 30 centimeters through this cylinder, this one will only go up 10 centimeters. So you get more force over here for the same pressure, but less movement. And this is how they lift cars in auto body shops or auto shops. They have a long, skinny piston on this side that they can push down on with a very small force, but on this side they have that huge piston underneath the car. Sometimes the thing's like 2 or 3 feet wide. And that huge cylinder with that huge piston in it gets all that pressure across the entire head, which allows it to have enough force to lift the entire car. Now in this case, 30 newtons is not enough to lift a car. You need something on the order of 30,000 newtons. So you need to push a little harder on this side and make this side a little bit bigger, but you'll eventually be able to lift the car, right? But that is how this works with hydraulics. You want to put your low force stuff on a small piston and the stuff that needs a high force on a large piston and cylinder, and then apply your smaller force to the smaller cylinder and piston, and the bigger force will come out the other end. This is how brakes work in a car. When you're pressing on your brakes in a car, you press on a small cylinder called the master cylinder, and that master cylinder is connected to a whole bunch of other cylinders that are much bigger at the brakes. So it applies a much larger force at the brakes. Most people assume that the master cylinder car must be the bigger one, but it's not, it's the smaller one. And the brake cylinders on each wheel, are much bigger and apply a much larger force on the brakes. Lots of things work out this way, not just these things. And that's exactly how they do this with the tractors. If we go back to our tractor picture here, maybe. If we go back to our tractor picture, you can see here that these cylinders are quite large and that these tubes back here can be quite small, because it doesn't matter. Way back at the very beginning of this system, there is a pump somewhere that is going to apply a pressure. It doesn't really matter what applies the pressure, but there's something that's going to apply a pressure into a small piece of tubing or a small cylinder along here somewhere, and it's back before all this stuff happens. That small force is going to exert a much larger force on this arm and allow you to dig a ditch or dig a hole or whatever you're going to be allowed to do with this backhoe. So that is the basic idea behind hydraulics. And like I said, there are myriad uses for hydraulics. You can even make crazy, funky cars with hydraulics. Here's a nice illustration of how brakes work. Now, it may not be obvious to you here that the master cylinder and the brake cylinders are much different in size, but they are, and they should be. They're just not shown here as such. But this cylinder here should be much smaller, but it's connected to all the brake cylinders. Right? It's a direct hydraulic connection. Let's see if we can't find another illustration that's nice for you here. Normal hydraulics. Lots of different examples of things I would have told you. That's okay. Anyway, so your hydraulics. Hydraulics is a very useful thing and very commonly used thing in engineering. So we need to understand how they work, and that's what we're doing in this project. So let's go back to our fluid power lab. I want you to remember that you need to put your name on this lab. Now, if you don't want to print this off, you don't have to. You can put your answers right in the lab. The way to do that is to go up here to the sign button on Adobe Reader and click the sign button, and then click on the add text button. Sorry, you can't do that. It's saying that I can't put a sign on it. Oh, yes, I can. I can add text to it, I think. I just can't save it. No, I can't even do that. Let's see if we can do it through commenting. Oh, dang it. So I guess it's got security features in it. So your other option is to print it off, or you can convert it to Microsoft Word online. That's usually something that takes quite a while. It's kind of a pain in the neck. You should also be able to save it as a different file. So if I save this, go over here to File and Save As a PDF, and I save it as my own thing, and save it as Jared, for example. And then I save it here in wherever I'm saving it, and let's save it on the desktop. And if I open it up again on the desktop, let's see if it's still secured. Still is, but I think I can change that. So I'm going to go to Properties, security. It's not going to let me change it for now. I don't know why. It should let me change it if I make it my own file. Go to properties here. Yeah. Apparently it won't let me write on it. So you can't write on it. Sorry, I lied. If you have Adobe Acrobat full pro version, you can do it, but you can't do it here. So we're stuck with just printing it off and writing on it that way. So, or converting it to a Microsoft Word document, which takes a while and has to be done. So let's not deal with commenting or signing or tools or any of this stuff. Let's just get rid of this crap. How do I do that? How do you open this up? Let's go back to where it was. There we go. Okay, so here we go. Apparently you can't write in it, so that's just tough luck for us. But let's look and see this. We've got the beginning of this this document splits fluid power into two different systems, hydraulics and pneumatics. Hydraulics is what we were just looking at, which uses a liquid, usually an oil. Pneumatics uses similar principles but uses air to transmit power. We're not going to be doing pneumatics project. Dealing with pneumatics is actually a little bit difficult and actually kind of dangerous in some cases. But they want you to list some devices that use pneumatics. Up here they've got a nail gun. I want you to find something different than that, right? They want you to list hydraulic devices. Up here they show a backhoe or just a mechanical shovel, whatever you want to call it. I want you to find a different one, right? Two different ones, actually, in each of those cases. Then they go on to talk about cylinders and how they're made, how they've got different ports on them. They've got a piston down the center and the cylinder in the middle. And oftentimes they have a mount on them so that they can be mounted to an object. And what's the point of the fluid ports? Well, that's where the fluid is going to come in so that the change in pressure can be felt in this cylinder, right? Sometimes the cylinders have a fluid port on both sides so that the cylinder can be pushed in either direction. Sometimes it only has it on one side because it only needs to be pushed in one direction. Depends on the system. In the case of tractors, it will have fluid ports on both sides because you want to be able to push and pull your tractor arms and not just allow gravity to do one or the other. Here they talk about the double-acting cylinders, and here they talk about single-acting cylinders, how they only have the fluid pressure on one side. And then they have some true and false questions here, I guess. Positive, negative, true, false, inward, outward. It's essentially just one answer or the other. And then down here, they show you how you're going to build a cylinder. We're going to be building a cylinder out of syringes, and so you're going to match up the things in the syringe, these different components in the syringe, A, B, C, D, E, with the different parts in the cylinder from the previous picture. So you're going to essentially be identifying the parts of your cylinders and pistons, which are syringes. Then they start to show you how these are going to be eventually used, right? We have cylinders that are going to be our master cylinders, 3 of them in this case. We have fluid lines. We have cylinders that are going to be our power cylinders at the other end, and so on and so forth. Then here they talk about pressure. Now this is where it begins to be a little bit mathematical. It does say that this class doesn't require any previous mathematical knowledge, but we're going to teach you what you need to know right here. So that's true still. It's just a little more, we're going a little bit beyond pale, I guess. Pressure is just equal to force divided by area. So if you apply 12 pounds of force over a 1 inch by 1 inch square area, then you get 12 pounds per square inch. 12 pounds being your force, 1 inch squared, or 1 times 1 inches, equals your area. If you apply the same force over inch over 2 inches by 2 inches, you get 2 inches by 2 inches, 2 times 2 is 4 inches squared, and you get 12 pounds per 4 inches squared, and you simplify the 12 over 4 into 3. So the same amount of force spread over more area gives you less pressure, right? And that actually is the reason why they don't allow people with high heels to walk in the gymnasium. Because people with high heels, instead of having 100 pounds spread over their entire shoe, they have 100 pounds spread onto one part of the shoe. And that exerts an extremely high pressure at one point on the floor, and it puts dimples in the basketball floor, and the basketball coach gets pissed off. Volleyball coach doesn't care so much, because in volleyball, you don't want your shoes to stick to the floor so much as you want your body to slide across the floor as you dive. So, anyway, that is that. And then here they talk about how you can actually feel those forces. If you apply a force to one end of a syringe and then press on the syringe and compress it, it doesn't hurt so much to press on it. However, if you apply that same force to the fat end of the syringe and put your hand on the skinny end will poke you and it can hurt. This is also the reason that we use knives to cut meat and not hammers to cut meat. Because a knife has a nice, very, very small cross-sectional edge, so that when you press on the knife, it applies an extreme amount of pressure at the edge of the knife, whereas a hammer spreads the same amount of pressure out over a much bigger area and just smashes the meat. Right? So they have lots of different examples here. And then they have some exercises where you can use the equation pressure equals force over area in many different ways. You can, if you know two of these things, you can find the third, in other words. And so you can use, they use this triangular chart where you have pressure, force, and area on this triangular chart, and you can use it to find one or the other, right? So if you cross out the one that you're trying to find, for example, then you can create an equation that gives you the other two. So if you cross out F, you have pressure and area next to each other in the chart, which means that pressure times area equals force. If you cross out the pressure, then you have force over area as your equation, because force is in the top here, force over area. If you cross out the area, then you have force over pressure. They actually have a typo here. This says area equals force over area. It's not. It's area equals force over pressure. So this needs to be replaced with pressure. But this little chart kind of helps you to solve these equations. Now, if it's no problem for you to just solve this equation for one of the variables, you don't have to go through that rigmarole. But if that confuses you, then you can use this chart to figure it out. But they essentially give you these three equations that you can use. If you want to find the force and you know the pressure in the area, use this one. If you want to find the pressure and you know the force in the area, use this one. If you want to find the area and you know the force and the pressure, then you use this one. You just have to make sure that this one's written correctly. This should be force over pressure. And then you can calculate the answer to this problem. Right? Calculate the force of the piston when the fluid applies 20 pounds per inch squared, which is the pressure, to the area that they give you, which is 1.5 inches squared. So they've given you the pressure and the area. You know, how do you calculate? Well, you know the pressure and the area, you multiply them together to get the force. So you can calculate that. Here they talk about measurements of pressure. There are two different units of pressure that are used regularly in the United States. Pounds per inch, pounds per square inch, PSI, or Pascal, which is newtons per meter squared. So a newton is about, like I said, it's about 2 pounds. Is that right? No, it's not 2 pounds. It's 0.2 pounds. 10 newtons is about 0.2 pounds. 1 newton is not very much weight. For example, I think I weigh 1,000 newtons or something like that. So 1 newton needs to be it's got to be about 0.2 pounds. 10 newtons is 2 pounds, whatever. That's not very much. 1 pound per square inch is actually a lot more pressure than a newton. But they're both measures of pressure. And then they go on to your first lab, where you're going to actually build a little piston machine that's going to lift a book eventually. So you're going to do some little experiments, you're going to measure some things, and then you're going to do that. So that is all I've got for you today to get you started on your first part of the pneumatic arm project. To go through this, you should work through at least half this worksheet. We got all the way through page 6 today, page 6, page 7, so you should be able to get those pages worked through, any of the things that need to be filled in, any of the questions that need to be answered, any of the activities that need to be done, and then a little bit more, I would expect. And then on Wednesday, we'll go through the rest of this so that you can be done with that Friday and we can start on the actual activity, the actual project. Do you have any questions about this particular activity? You guys good there in Stapleton? Give me a thumbs up in Stapleton if you're good to go. Can you guys hear me in Stapleton? You guys good to go in Stapleton? Okay, well, for some reason they're not answering me back. But anyway, we'll see you guys later. Put an end to that presentation.